So welcome to the fourth video in Gravitation. This will be a very brief video looking at the gravitational potential energy of an object in a changing gravitational field. So in the last video, we looked at how Newton's law of gravitation applies to us here on Earth and how it matches up with what we already know. Our acceleration due to gravity on Earth is equal to 9.81 meters per second squared. In this video, we'll look at the gravitational potential energy now applied on a much larger scale, so on a universal scale. After this video, we'll have a look at Kepler's planetary laws, and then we'll return to looking at the energy in conjunction with various different orbits. So we know that an object in a gravitational field can have a potential energy due to that field, which we know, oddly enough, is called the gravitational potential energy. So here we're going to have a look at the gravitational potential energy for a planet of mass m at a distance of capital R from a larger planet, which is mass capital M. I have defined the direction along the radial axis r, little r, as positive and pointing outwards. In the work and energy topic, we saw that the work done on an object was equal to the negative of the change in the potential energy of that object. We're interested in the potential energy of our object at radius r, capital R. And what we have is an expression for the change in the potential energy. So we can use the fact that at a distance of infinity from our large object, there is no longer any force due to gravity. That is, the gravitational potential energy at infinity is zero. So if we look at the work required to move our object from its current position at the distance of capital R out of the influence of the gravitational field to a distance of infinity, we find that work done is equal to the gravitational potential energy at a distance of r. So this is the quantity that we want. So now to find that quantity, we need to calculate the work done on the small planet by the gravitational field. So work is equal to F dot S, and if this isn't a familiar equation, I would suggest a review of the work and energy topic. In the case of a constant force acting, so for example, the gravitational field at a fixed radius, or for example on the surface of the Earth, then we can say that the work, or our gravitational potential energy, is equal to the force due to gravity times the displacement of our object in the direction of that force. Or in more familiar terms, that's the mgh equation. But here, we're working at a large distance r, and the force due to gravity as we change r over this kind of distance is not constant. So we're dealing with the work done by a variable force. So we do our usual trick. We look at the work done over a very small distance ds, or very small displacement ds, over which we can assume that the force is constant. So in this case, our small amount of work done over this distance, which is dw, is equal to F times our small displacement ds. And then we integrate that over our region of interest. So in this case, our work done varies as a function of r, our distance in the radial direction, and we're interested in how much work needs to be done from the current position capital R up to infinity. So we integrate our force due to gravity over that region from r to infinity. We know that our formula for gravity is gmm on r squared, and then we just solve the integral to find that the total work done is equal to negative gmm on r. So we can say that in the general case of an object located at some distance r from a mass m, the potential energy is equal to negative gmm on r.